Hello. In today's video, we'll be exploring the topic of the MGF, or rather the moment generating function. We will be showing what the moment generating function achieves, and we will be proving the moment generating function through a Taylor series expansion of it. We will be further showing the moment generating function of a normal distribution and how we get to that. And that's it. So without further ado, let's begin. We'll begin by defining what the moment generating function is, which is the expectation of e to the power of k multiplied by x, where k is simply a parameter and x is simply a distribution. In our case, x will be the normal distribution. So let's just set that to be the normal distribution. And from basic statistics, we know that the expectation of something, so in our case, the expectation of e to the power of kx, is the integral. And from going from negative infinity to positive infinity, since we assume that x in our case is a normal distribution, multiplied by that thing, so the integral of the object which we're trying to find the mean of, which in this case is the e to the power of k multiplied by x, multiplied by the density function of that object which we're trying to find the mean of. And yeah, so some people might get confused as to why the density function of e to the power of k multiplied by x is the density function of x. Well, this is partly due to the law of the unconscious statistician, which is often ignored in mathematics, or rather not ignored, but assumed without rigorous proof. And the lotus, or the law of the unconscious statistician, basically states that a transformation of the variable, which in this case is x, so let's assume the transformation is g of x, has the same density of x. I'm obviously simplifying it, but the purpose of this video is not to get into this very deeply, but that's just something that if you have a question, then that's the reason that we use the density function of x as the density function of e to the power of k multiplied by x. So let's move on. So what does the moment generating function state? Well, the moment generating function states that if we take the derivative of the moment generating function of order m with respect to k and set k equal to 0, then we would be able to obtain a raw moment of order n. So the way that we can prove the moment generating function is through approximating that moment generating function using a Taylor series expansion, which we will do in just a minute. But before we just get into that, I'd like to explain why the moment generating function is useful and what is the purpose of it. Because if we would like to find say the mean of e to the power of k multiplied by x, well, we can simply take the integral as shown over here. And if you want to figure out, for example, the variance, well, we know that the variance is equal to the expectation of x squared minus the expectation of x all squared. So what we'd have to do is take the expectation of x squared and take integrals of that in order to be able to figure out the variance, etc. So this could also be assumed if you would like to find the skewness or the kurtosis of a distribution, So that's what we would generally do. But with the moment generating function, what it allows us is that we don't have to go through the cumbersome task of taking integrals to find the expectation of x to the power of m, but rather we can simply, using this law over here, evaluate the moments. So let's refresh on the Taylor series expansion. So what is the Taylor series expansion? Well, the Taylor series expansion is the sum going from I equal to 0 to n equals infinity of the derivative of order n of the function which we are trying to approximate, evaluated at point C, where C is basically any point on the x-axis, multiplied by x minus c to the power of n over n factorial. And that is the Taylor series famous expansion. And all it's doing is approximating the function, which in our case, what we were trying to do is approximate the moment generating function. We don't really need all the variables from I equal to 0 to infinity. Obviously, that will increase our accuracy. However, the accuracy of the Taylor series expansion is very, very high and quite sufficient up to order, say, 3 or 4. So we don't really actually need to sum all of this infinitely. So we can rewrite this Taylor series expansion in a more compact way, which will not take too much out of the approximation. So, but before we do that, actually, we will set c equals to 0. And that will give us something which is known as the Maclaurin series expansion. And therefore, this will become much more nicely compacted as equal to the sum going from I is equal to 0 to n is equal to infinity of the derivative of order n evaluated at 0, since we set c is equal to 0, multiplied by x to the power of n, since now x minus c, where c is equal to 0, so we simply have x to the power of n, and over n factorial. And that's the Maclaurin series, and that's what we will be using to prove the moment generating function. So as I was saying just previously, we were going to try to get this in a more compact form, so up to third or fourth order of n. So we'll start at the starting point, which is 0. So what is this at time equals, not time. What is this at n is equal to 0? So, well, we will have the function. In this case, the function is not, we're not taking the derivative because we don't have the first derivative. We're simply having the function over here. So the function evaluated at point 0 multiplied by x to the power of 0 over 0 factorial. Continuing on, we would have the first derivative now multiplied by x, and this is 1 over here, 1 factorial. And then the second derivative evaluated at 0 multiplied by x squared over 2 factorial. And we'll just do one more. So that will be the third derivative evaluated at 0 multiplied by x cubed divided by 3 factorial. So this over here can simply be rewritten as the function evaluated at x at the x-axis equals 0, and this part of the function can also be slightly compacted as the first derivative of that function evaluated at 0 multiplied by x, and the denominator is simply 1 factorial, which is equal to 1, so we don't actually have to write it down. And this over here would simply be as is. So now let's just try to get the Taylor series expansion of the moment generating function. So we will start by taking the Taylor series expansion of e to the power of k of x, and then once we do that, we will simply take the expectation of the Taylor series expansion, and that would give us the moment generating function's Taylor series expansion. So currently we're not actually taking the Taylor series expansion of the moment generating function, but rather only this part of it. So let's do so. So at 0, the function is equal to simply 1, because e to the power of 0 is equal to 1, plus the derivative of that. So and setting x is equal to 0 would give us e to the power of k multiplied by 0 multiplied by x, and this e to the power of k multiplied by 0 is simply equals to 1, so we can simply delete that and just write x over here. And next we would have the second derivative, so therefore we would have k squared e to the power of k0 multiplied by x squared over 2 factorial, which again, this part of the equation can disappear, or rather become equals to 1, because e to the power of 0 is equal to 1. I'll just move that x squared a little bit closer to be neat over here. And following the same logic, we get that the third derivative component would be simply equal to the following. Now we're going to take the expectation on both sides, and that will lead us to the Taylor series expansion of the moment generating function. So let's do that. That's what would happen once we simply take the expectation on both sides. So let's now just move on to a different page. And what we're going to do next is prove that this holds true. Okay, so what we're going to be doing is we're going to take the derivative of the moment generating function, but in this case we're going to take the derivative of the approximation of the moment generating function, which we found out through the Taylor series expansion. So we're going to take the derivative of this with respect to k and set k equal to 0, and see that we arrive at the raw moments of order m, depending on how many times we took the derivative of that approximation. So let's attempt that. So we will take the derivative of the expectation of e to the power of k multiplied by x. And for starters, we will take it with respect to the first derivative. So what we will do, just looking back over here, if we take the derivative of this with respect to k, so the 1, that will lead us to simply having 0. If we take this derivative of this with respect to k, we would be left with the expectation of x. And if we take this component's derivative with respect to x, what we would get is the following. And over here, again, if we take the derivative of this component with respect to k and set respect to k, we would get the following. So we would get 3k squared, the expectation of x cubed over 3 factorial. And now remember that the moment generating function, to get raw moments from it, we would take the derivative of it with respect to k and set k equal to 0. So let's do that. What we would arrive at is that this will equal to 0, and therefore this whole function will go to 0. And if we set k, or again over here, equal to 0, then this whole function will be equal to 0. And therefore, taking the first derivative of the moment generating function with respect to k and setting k equal to 0 does give us the expectation of x, which is the first raw moment. Okay, let's attempt that again, but we will now take the second derivative. So let me just back up over here. And what we're going to do now is take the second derivative. So recall we already took the first derivative. So now taking the second derivative of this, well, this will disappear now. And over here, that k will consequently disappear. Or rather, sorry, not disappear, it will be equal to 1. And over here, once we take the second derivative, we'll be left with 2 multiplied by 3. Well, I'll just write the 2 over here, multiplied by 2. And this is the second derivative with respect to k. And setting k equal to 0 again, we would find that this will go to 0 since there's a k over here. And what we'd be left with is 2 multiplied by the expectation of x squared over 2 factorial. And 2 factorial is simply equal to 2. So therefore, those two cancel out with each other. And we'll be left with the fact that the second derivative of the moment generating function with respect to k, while setting k equal to 0, does indeed yield that it is equal to the expectation of x squared, i.e. the second raw moment. So let's attempt this one more time for the third derivative. So let's do so. If we take the third derivative, well, we're taking, remember, this is the equation for the first derivative, so we had to take the derivative 2 more times to get it, to basically get us the third derivative. Well, taking the third derivative, this will yield basically 0, and this will give us 0 because if we take the derivative 2 times with respect to k, then there is no more there's not going to be a k on the second time we're taking the derivative, so this will get to 0. And over here what we would get is by taking the derivative 2 times over here, we would get multiplied by 2, and then for the second time this will simply equal to 1. Taking the derivative of this with respect to k will give us 1. So this is what we'd be left with. And now the 3 factorial is basically equal to 3 multiplied by 2 multiplied by 1. And hence those cancel out, and we do find ourselves getting that the third derivative of the moment generating function with respect to k, setting k equals to 0, does give us the third raw moment. I hope that this has shown you how the moment generating function basically enables a person to get any higher order moment, raw moments from the function that he is trying to evaluate. And it is basically a very easy way to get those raw moments if that is your goal, rather than going through the cumbersome task of taking integrals. So we will now apply the moment generating function to the normal distribution, and we will show how to obtain the moment generating function of the normal distribution. So let's begin. Now recall the density function of the normal distribution. So that is equal to 1 over the square root of 2 pi sigma squared multiplied by e to the power of -1/2 multiplied by x minus mu divided by sigma all squared. And that is the PDF of a normal distribution. So the reason why I'm obviously writing the PDF is because we require it to solve the expectation of a normal distribution. However, now we are no longer computing trying to compute the expectation of x, but we're trying to find the expectation of e to the power of k of x, i.e. the moment generating function. So let's do that. So what we need to evaluate is the following, which is equal to the integral going from negative to positive infinity, because these are the bounds of the normal distribution. The integral of the value which we are trying to compute the mean of, which in this case is equal to e to the power of k multiplied by x, multiplied by the density function, which in our case is equal to the density of x. So what we would have is 1 over the square root of 2 pi sigma squared e to the power of -1/2 x minus mu divided by sigma, all of which is squared. Now, what we're going to try to do is we will try to combine the e to the power of k multiplied by x with this portion over here. So basically we're going to combine the exponents together, and the main goal behind this is to figure out a way where we can get basically this format to evaluate the normal distribution even after adding kx to the exponent. So let's just simply focus on the exponent part. We will ignore the integrals and the 1 over the square root of 2 pi sigma squared, and we'll just focus on the exponent part of it. So let's do that. So first we have kx, just delete the plus sign beside it. So we have kx, and we have minus 1 over 2, and I will move that sigma outside the brackets so that I can expand this squared over here. So if I take it outside, then I have to square it because it was squared outside. There's a square over here. So if I take it outside, I have to square it. And I would have to multiply it by this. And now I'm going to expand that formula over here. So expanding it yields the following. And now, as I said, the objective is to be able to represent this whole equation as something of the format equals to this, so that we can evaluate the normal distribution. So, what we will do is we will first move the this component inside the brackets. And to move it inside the brackets, I would have to multiply it by negative 2 sigma squared, so that I account for the negative half sigma squared, which is outside the bracket. So let's do that. Okay, so now that I have done that, I realize that, okay, those two could be combined together. The reason that I'm trying to do it is, again, I'm trying to get it in the format of this. So I'm trying to first be able to get it to this format so that eventually I can get it to this compact format, which the normal distribution is very famously known as. So what I will do is I will have negative 2 x, as both of them have negative 2x, and then that will be u plus k sigma squared, and that is the combination of this section and this section. Then I would have plus u squared. Now, in order for it to be of that squared format, I would have to have this section over here, so that basically we have the square of this portion over here, because the square of x, we have it on this side, so it's x squared, and now we have to have the square of u plus k sigma squared, and we already had one proportion of that, but it was not complete. So in order to complete it, I simply added k squared sigma to the fourth plus 2u k sigma squared, because that's from basic mathematics. If you square, if you want basically the squared of this, then you'd have to have this squared plus 2 multiplied by that component multiplied by that component plus this component all squared. So now that we've done that, we need to subtract what we've added so that the formula still holds. So what we're going to do is have a negative k squared sigma squared minus 2 u k sigma squared, because since I added those to the equation, I have to subtract them so that the equation still is valid. And now that I've done that, I can combine, I can take this proportion outside of the equation. So what I'd be left with is negative 1 over 2 sigma squared and x minus u plus k sigma squared. And taking this out, I have to basically multiply it by the factor which is being multiplied by the brackets. So if I want to take it out of the brackets, I have to account for the thing which is being multiplied by. So to do so, I will have to have a positive sign, because the negative multiplied by a negative gives me positive. And I would have k squared this is to the power of 4. Apologies, I did not copy it quite rightly over here. So that will give us k squared over so k squared multiplied by sigma squared over 2. That's what happens when I multiply this component by that component over here. And for when I multiply this by this over here to get it outside the brackets, basically, what I'd be left with is uk. And therefore, let's now return to the full equation. What we have managed to do is get this equation in the format of, let me just write it down. Is equal to e to the power of So all that happened over here is that I separated this component to be split again from the e's. So now I basically removed it outside to be by itself, and I could move it outside of the integral over here, because it does not depend on the integral over here, since these are all simply parameters. K, as mentioned before, is a parameter, as well as sigma. So I could take it outside, and the 1 over and basically what we have over here is simply the PDF of the normal distribution. And over here, all that's happened is that mu, which is the mean of the normal distribution, has been shifted by a value of k sigma squared. So all that happened was that the mean was shifted. However, taking the integral of the normal distribution from negative infinity to positive infinity, even if the mean was shifted, is simply equal to 1. So the moment generating function ends up to be equal to the e to the power of k squared multiplied by sigma squared over 2 plus uk, as this component over here evaluates to simply equal 1. So the moment generating function of the normal distribution is equal to the following. And if I take the derivative of that with respect to k and set k equal to 0, well, what we'd get is take the derivative of that. So that will be 2k sigma squared over 2 and setting k equal to 0. Therefore, this would evaluate to 0, and this over here would evaluate to basically, the exponent would evaluate to 0. So we would have e to the power of 0, which is equal to 1, and 1 multiplied by mu is simply equal to mu. And therefore, the derivative of the moment generating function, the first derivative of the moment generating function of the normal distribution with respect to k, setting k equal to 0, gives us mu. And that is indeed the expectation of x, i.e. the first raw moment. So we can, there's also one other factor that I should explain when dealing with the moment generating function, is that there is also something called the cumulant moment generating function, and that basically allows us to get, instead of raw moments, which is what the MGF provides, we would get the central moments. So, for example, we would be able to get the expectation of x minus the expectation so it is the expectation of all of x minus the expectation of x, and that would basically allow us to evaluate things such as variance more easily, rather than just having the raw moments. And the way to get the cumulants of the moment generating function is by simply taking the log of the moment generating function. So in this case, we would basically have the following. Taking the log of the MGF would give us and setting k equals to 0 would give us simply taking the derivative of that first, so that's log. Now taking the derivative of that with respect to k and setting k equals to 0 would give us mu, which is indeed the first central moment. And that's basically the case. If we would like, for example, the central moment of order 2, then what we'd have to do is take the derivative of the cumulant function with respect to k twice. And to do so, if we take that, we would have sigma squared, and that's it. And that will basically, and that aligns to the fact that we have this to be our second order central moment. Thank you very much for listening. I hope this was somewhat informative. And yeah, if you have any questions, you can ask in the comments.